Now I get to introduce Chris Lintott from Christopher Ranger, Christopher Lintott. And I'm going to give you a microphone. So, Chris comes from Oxford, from the next building to me, and we work together, but that is not why I chose him. It wasn't a matter of convenience. We've chosen Chris as the opening keynote because it really is in that fourth quadrant of the earlier picture. It's all about the engagement of the citizen. We've just heard what Thomas Bodley has to say about the Republic of Letters. It really sets the tone for the discussions. If we want to understand what the future of libraries, the future of publishing, and the future of research are, we have to understand how research is done in the future, how scholars are working, how citizen scholars are working. And that's why we have Chris up as our first speaker. Several of you will, from the UK, be aware of Chris already from his presence in the media, for example. And I don't need to do any more introduction than that, so I'm just going to hand over.
Thank you. It's excellent to be here. I've had a theory for a while that all conferences should have at least one astronomer. So thank you for sticking to this. Hang on 2 seconds. Am I really going to have to hold this? I'm one of the non-technical astronomers, as you can tell. Got it. Does this work? Yeah, that'll work. Good. Excellent. Sometimes the simple technology is the best, right? I'm delighted to be here. This is a conference that has a stellar reputation and an intimidating and mixed group of people. So I will try to be interesting to as many of you as possible. I note, Dave, that one thing that doesn't change in the future of scholarly communication is that we're 20 minutes late already. And so I will stick to tradition and try and make sure you get to coffee on time. This may mean that I have to go very fast, do interrupt me, do stop me, do shout from the back and say if you'd rather hear more about something. But yes, everything I'm going to talk about is based on the idea of citizen science, and the ammonite that's on the screen at the minute is a reminder that this is a very old idea. If you go to, as you've just heard, you know, the foundations of many of our sciences are based on the idea that anyone can contribute, and this is particularly true in the observational sciences. So in paleontology and geology and ornithology and astronomy, it was vast networks of amateurs, particularly in the 19th century, that made it possible to get data sets together for scientists, professional or otherwise, to analyse. And it's really only in the 20th century that we get this idea of a professional cohort of scientists in their ivory laboratories, or whatever the analogy is, excluding the public from a technical scientific process. But that is what happened, and hence the coinage of citizen science. In contrast to that, we actually found, thanks to the Oxford English Dictionary, including citizen science, we now know the first reference we think of is from New Scientist in the 70s, 1979, beautifully in an article about UFOs. But what's nice about this is this contrast between the citizen scientist in the past, the amateur investigator who contributed substantially, versus the specialisation of modern science. And this is exactly what happened in my field. I grew up with a small telescope, wanting to make discoveries myself. And as I moved through the academic system, I realised that astronomy doesn't work like that anymore. What people do is they build experiments. And the canonical example is this thing. This is a 2-metre telescope called the Sloan Digital Sky Survey, which is up in New Mexico. Very similar climate to Oxford, so about 300 clear nights a year, though slightly less light pollution. Now I know how many of you have been here before. And Sloan was a marvellous thing. It was built to map the nearby universe. And for most of the time, all it did was point upwards and allow the sky to turn over it. And as things progressed through its field of view, over 8 years, it recorded the positions of about 350 million objects. And of those, about 1 million of them seem to be the faint, fuzzy things that we call galaxies. Galaxies, of course, an immense system of stars and gas and dust and dark matter and so on. And for 1 million of those objects, on the clearest nights, Sloan went back to them and it measured the distance as well. So this is a 3-dimensional map of our local universe. And we can see what that looks like. We're going to start. I don't know if we can kill the lights for this. No, I'm probably just going to break stuff. Never mind. Oh, look, lighting control. Stage dark. Let's see if that works. There we go. The universe is best seen in the dark. And so we're going to start on the Milky Way, our own galaxy, and travel outwards through about half of the Sloan survey. And what you see first is that space is pretty empty. There's a lot of space between the galaxies. But as we get further out, we get this rather remarkable result, which is that space on the largest scales that we can survey is lumpy. There are places where there are loads of galaxies, and there are places where there are very few galaxies. There's a thing up here on the left, there's a C-shaped structure which is called the Sloan Great Wall, and it's the largest structure that we know of. And actually, modern astrophysics, it can be parsed as an attempt to understand why we ended up with this sort of lumpy cosmic web structure. We can do that in a few ways. We can look at the behavior of the system over very large scales, so we could sort of take this as a whole and understand the properties of this object. Or we can look at the individual galaxies and compare them to what we might expect. This will rotate in a second. And I should point out the gaps here. The reason this is a bow tie isn't because that's the shape of the universe. The black bits are sort of here be dragons. This is the bit of the map that isn't filled in yet. But the point is we can look at these galaxies individually, and we can parameterize them, and we can compare where we see them in the universe to our expectations, our theories, and our simulations. So if you have two galaxies like these, we can parameterize them by their mass. That's easy to measure. We can parameterize them by color. That tells you about the recent star formation. But the most obvious difference between these galaxies is their shape. And these are two different shapes. And it turns out that that measure, the idea that galaxies come in different shapes, tells you about their history over the last few billion years. The shape is dictated by the orbits of the stars which make up these galaxies. And so if you can identify a galaxy by shape, then you know something about what's happened to it. You know whether and when it's formed stars, you know how it's interacted with its surroundings and with other galaxies. And it really is a deep and fundamental measurement. And astronomers have known this since the 1930s. Edwin Hubble, for whom the telescope was named, wrote a wonderful book on the shapes of galaxies. And for most of the 20th century, astronomers would assemble small numbers of high-quality images. And if you were an eminent professor, you could publish an atlas of galaxies, which explained your own personal classification scheme. And then we could argue about whether... I'm just going to try and put the lights back on. Yay. Is that too much? Probably. And so, as a professor, you could then have a happy argument for the rest of your career with your colleagues about whether this particular galaxy was an SC type 2 or type 3, or whether it was an SD, and so on. And the classification was something that was owned by the very top experts in the field. And in fact, there are papers that show you could trace the choices that people make about how to classify galaxies based on who their PhD supervisor was. So there's this idea of inherited expertise. By the 1980s, surveys got large enough that there were thousands of galaxies that were worth classifying. And suddenly the field discovered that you didn't need to be an expert, but a PhD student would do nicely. And students started their theses by working through plates, photographic plates, and classifying thousands of galaxies. And no one questioned those classifications, because otherwise we'd have to do it again ourselves. And so that worked, but people could see that things like Sloan, the survey I've been talking about, were coming. And there was an effort made to develop machine learning techniques to get to grips with this problem. And astronomers quickly discovered that it's very easy to build something like a neural network that could split galaxies. Let's just take the simple problem. Let's split them into these two types. So a nice big spiral galaxy like the one on the left, or a ball of stars that we call an elliptical on the right. Even with that simple problem, it's very easy to train a neural network to get 70% accuracy. After 3 years of work, sort of a PhD thesis, you get to 80%. But the kind of effects that we're looking for are down in the 1% and 2% level. And so this is nowhere near sufficient to classify these large systems of galaxies. And it's almost worse than that, because you don't really, with those systems, you don't know which 30% you've got wrong. So it's quite hard. You can't even give most of the task to a machine and then hand the rest over to computers. this remains a problem. This sort of fuzzy pattern recognition remains a problem that humans beat computers at. And when I first arrived in Oxford in 2006, there was a student called Kevin Shawinski who had just classified 50,000 galaxies by eye. And we worked with Kevin on this dataset, and he'd proven that he was better than a computer. But it became apparent that that wasn't enough, that we needed to go through the other 950,000 galaxies in the sample. And no matter how much beer I bought Kevin in the Royal Oak just opposite, he refused to contemplate this possibility. So the first result of Kevin's thesis was that a student will classify 50,000 before they tell you where to stick the rest of your galaxies. And so we needed a different solution. And we could have spent years going for the next increment in machine learning and so on, maybe pushing it to 85% accuracy. We could have done what other colleagues did and start denying that the shape of the galaxy is important at all. There's a surprisingly rich literature on that. What we did instead was we asked for help. And inspired by a few previous projects, we built a very simple website called Galaxy Zoo. And the Galaxy Zoo website gave you a picture of a galaxy, and its first incarnation, it gave you 6 buttons. It asked you whether it was a spiral galaxy or an elliptical galaxy. For various reasons we'll get into, or we can get into later, we asked which way the spiral arms were turning. There's a button for a merger and a button for this being a star. And the idea was that this would be a side project, that I'd go and talk to amateur astronomy groups. Maybe 50 people would go home and do 50 classifications. And we thought in 5 years we'd work our way through the million galaxies. But it turns out the internet doesn't work like that. It's very hard to succeed slowly on the net. You either fail utterly or succeed beyond your wildest dreams. And by the end of the second day, we were doing 70,000 galaxy classifications an hour. For those who know the technical language, that's 1 Kevin month per hour. The Kevin month being the unit of galaxy classification, of course. And so this was remarkable, and we haven't quite gone on at that speed. But Galaxy Zoo has received about 300 million separate classifications since 2007, and we now ask more detailed questions, and we've looked at other surveys and so on. But you shouldn't be impressed by that, because you also need the piece of information, which is that the classifications taken collectively are very good. And we can indeed split these galaxies into their constituent types, just as we wanted to. We've got elliptical galaxies, clockwise galaxies, and anti-clockwise galaxies. And because we've had lots of people look at each one, we also have an estimate of confidence here. For each of these galaxies, I don't just know that I think it's a spiral. I know that 10 out of 10 people said it was a spiral, or 8 out of 10 people said it was a spiral. This sort of fuzzy knowledge about the classification turns out to be incredibly useful, both for doing the science, but also for going on and training machines. And if I get time at the end, I'll talk more about that. So citizen science in this form is almost treatable as a black box. You have to find your volunteers, you set up your question nicely, you test that you're getting the answers that you want, and you press go. And it's almost like running a machine learning routine on your data, because you get answers back with a probability of classification at the end. And that's a well-designed experiment. And that, when we set Galaxy Zoo up, was what we were thinking about. However, one of the interesting things that happens when you get hundreds of thousands of people involved in this sort of project, and Galaxy Zoo has had about 600,000 participants over the last 5 or so years. Each one of those people is, of course, a unique individual. So here's a randomly selected Galaxy Zoo user. Actually, this is a postdoc from Imperial College, who some of you may know. This is Brian May, who is incidentally one of the world's experts on dust in the solar system. So Brian was supposed to finish his PhD in the late 70s, but got distracted by some other career. Spent 30 years doing this kind of nonsense. And then around the time we launched Galaxy Zoo, had just come back to astronomy. To his immense credit, Imperial had offered him an honorary degree, and he'd said that he'd actually rather finish his thesis. And a key, if you're going to take 30 years out of your research career, is to pick a problem that's either difficult enough or boring enough that it will still be there 30 years later. And Brian had achieved that, and so he was getting back into astronomy, and I had to teach, I knew him vaguely, and I ended up teaching him how to use things like the archive. or to write in LaTeX, and all the modern tools of science communication that this conference is trying to build on. And in return, he wrote about Galaxy Zoo on his blog, creating a permanent bias in the musical taste of Galaxy Zoo classifiers. One of the people who read that blog is this woman. This is Honey van Arkel. She was a school teacher in the Netherlands. You can see she has a guitar that's very like Brian's. And if Brian said classify galaxies, that she was going to classify galaxies. And she became the first person to see this image, which is an image drawn from the Sloan Digital Sky Survey. And this, I think, illustrates the advantage, the real advantage of human classification, something we hadn't anticipated, which is that if you're a neural network, an artificial neural network, looking at this image, and you're really good at galaxy classification, you might be able to tell me that that galaxy at the top is a spiral. You can just about see the two spiral arms there, and there's a dust line going across. But the people in the room will be wondering what the blue blob is. It's exactly what Honey asked, and she called it a voorwerp, which is, we thought was a technical term, but is actually Dutch for object, or thingy, more colloquially. But we managed to get this into the literature. So this is the official name of this object is now Honey's voorwerp, and it's a fascinating thing. Here's what it looks like with the Hubble Space Telescope. Never mind the shift in colour, we've just used different filters. But it's an amazing thing. It's at the same distance as this galaxy. So it's large. It's a galaxy-sized gas cloud. It's heated to 50,000 degrees, about 10 times the temperature of the surface of the sun, but it has no stars in it. And so it became this detective story to try and work out what it was. And it turns out it's actually been energized by a jet of material expelled from a disk that's falling onto a black hole at the center of this galaxy. And it's a hugely exciting and unique object. And we didn't even know to look for these things. So one of the key advantages that citizen science gives us is it brings back the idea of serendipitous discoveries into large data sets. So we're still doing the sort of experiment, the let's find all the spiral galaxies, but we also get the weird and the wonderful, thanks to this sort of very human ability to be distracted while working through this. And anomaly detection in this form is very difficult to automate, especially when you're also optimizing for standard classification, whereas humans could do that very, very easily. And so this serendipitous discovery became a key feature of the advantages that Galaxy Zoo gave us. And we started to think about what those might be and how our community distributed itself. So we started to do sort of basic statistics. So this is the distribution of effort in Galaxy Zoo. So each box here represents a volunteer. And you can see we're heavily dependent on some super users over here. These are people who've seen next to first order all the galaxies, many more than Kevin looked at. But there's also a substantial amount of effort from people who just come by once or twice. And this has become a design principle. We want to appeal to these people, partly because they become these people, but also because there's substantial effort just from people coming past and making an authentic contribution to science very quickly. We've also shown that taking part in these projects isn't just a way of producing science, it has effects on those who are taking part. So we did a longitudinal study where we put questions into the site, questions about basic astronomical and galaxy formation topics at the sort of level that you teach in Astronomy 101 in the States. And we, in fact, calibrated this survey against a bunch of Astronomy 101 students. And I can show you that the longer somebody spends doing Galaxy Zoo, the more they know about galaxies and about astronomy. And that might not seem too surprising, but we can show that they learn things that we do not teach them on the site. So the kind of information that they're picking up, they're not getting by doing a thorough job at Galaxy Zoo. So Galaxy Zoo is acting as an engine of motivation. It's inspiring people to go out to get more astronomical knowledge from elsewhere, presumably on the web, but perhaps also in real life. And they're bringing that back to their citizen science. And I think this is really, really interesting when combined with the fact that the people we're reaching aren't the amateur astronomers that we expected to be targeting. They're there, they're helpful, they play all sorts of roles. But most of the people who come to our site are what we'd call science attentive. So these are people who would read a science story in the paper if they came across one, but they're not subscribing to Scientific American or New Scientist. They're not seeking out science museums when traveling. And that's a very different audience for me to communicate to. These aren't the people who come to a public lecture if I stand on the stage and tell them about the wonderful things that I've been doing. They're inspired more by the fact that they can get involved. Of course, it will have occurred to many of you that nothing I've said, really, apart from perhaps the details of the Volvo and Brian May's involvement, is at all specific to astronomy. And one can play this game with all sorts of data sets. And in fact, one of the other things that happened is we started to get phone calls from other researchers saying, you know, you're people who look at galaxies. Do you think they'd help with my penguins, for example? And so a recent example of a project is, another Oxford one, is Penguin Watch. I recommend this during sessions, it's very therapeutic. So Penguin Watch is the result of putting these are time-sensitive cameras in penguin nesting sites. So these cameras typically take pictures every 5 minutes to get a proper census of activity at these large colonies in Antarctica. So in the past, these things have been studied by a researcher who would visit once or twice a year, but cheap cameras now exist that can survive for the entire winter. And so early discoveries from this program, led by Tom Hart from the Department of Zoology here, include the fact that penguins nest much earlier than expected. And these colonies are highly sensitive to climate change, which is one reason to study them. And you can see the user interface is well done, I think, but it's nothing special. The original name for this project was Penguin Hunters, but they weren't having any of it. And it's the same thing. So we launched this project a month or so ago, and we reached our millionth penguin at the weekend. So it turns out that to an astronomer, the thing that shocks me is that there are loads of penguins. I don't know if that's a publishable result. But we've also done a lot to support Tom and his team, because it turns out that if you design these projects badly, you take a set of images that no one has time to look at, and you create a large database that the researchers you're working with don't have the skills to use. You know, the Penguin Watch already has 1 million entries in its database. And so we take on the task of clustering for them. So this is the result of an algorithm that takes the clicks from multiple people and decides where the penguins actually are. So we've started to have to do that data reduction in-house in order to support the efforts of the scientists who want to use our platform. And that's been a critical learning curve. The original assumption was that scientists would want the raw data themselves and to go from clicks to classifications. That task of taking 10 people have said these different things about this image to a conclusion. We thought that was something that domain-specific scientists would want to do, but actually it's the task that's shared across Galaxy Zoo, Penguin Watch, and many other projects, and it's something we've had to take on. To give you an idea of the range, we can go from penguins to particle physics. This is an image from the Atlas detector. So you're looking at a cross-section here of the Large Hadron Collider beam. This is the result of a specific collision. This image was one of the ones, so we have a project looking through these images. And this is fascinating to me because the Large Hadron Collider teams have dealt with the deluge of data that they get by essentially throwing more than 99% of it out. So they have a set of triggers that look for events that they're expecting. And if the collision in question hits one of those triggers, then it's saved. But most of the data and most of the collisions of particles never hit a hard drive. There's just not time, there's not space to do that. And that means that if there's unusual physics going on at the LHC, most of it will remain invisible. So let's say a new type of particle that's not expected is being created. That will show up only as a loss of energy compared to the channels that they are expecting. And if you wanted to go back and look at those particles, you'd have to run the whole experiment again, because you'd have to change your triggers to capture the data. But they do save a small amount of random data. And so Higgs Hunters is the project, is a way of looking through that data just to see what might be there. And we're doing it for two reasons. One is because that's an interesting science case, and the scientists told us that it was something they had to do themselves, and they didn't have time to look at even the small amount of data that was saved. But the second reason is an experiment in citizen science. This project will almost certainly fail to find anything interesting. But if it does find something, it'll be a Nobel Prize. And so it's interesting to think about, we know that the Galaxy Zoo volunteers are incentivized by making a real contribution to science. When we survey them, they tell us that they want to do something that's real. And we can show that because when we shut down projects and put a little sign on the front that says you can still browse, but we're done with your science for now, people stop. So the question is, this is science, but the odds of it succeeding are incredibly high. In fact, so high that I don't think any professional would spend their time doing this. There are other things to do if you're a particle physicist. And so we're interested in how our community reacts. That said, on the first day this project ran, if any of you are particle physicists, you'll be very excited by this image. We got this email from the PI, and this is the kind of thing you want. It begins, "Who's messing with us?" This is a jet of muons predicted in some beyond the standard model theories, but it's never been seen in the wild. I don't remember us putting anything like this into the simulation. Now, it turns out that this is actually a different event. It's called a breakthrough, and it's normal particles that escape. But for about half an hour, I thought we'd succeeded on the first try, which would have ruined my citizen science experiment. But nonetheless, it's fun to try. And we can even go beyond science, of course. So launching this week in beta is what we're calling the Planetary Response Network, which is an effort to take this stuff and try to do near-live follow-up of disasters like typhoons hitting, in this case, the Philippines. We have a partnership with a bunch of people who can get us satellite images very quickly, and with aid agencies on the ground who need to pass that information very quickly. Now, all of these projects sit under the umbrella of the Zooniverse, zooniverse.org, which now has a registered community of about 1.3 million volunteers. Here's how they're distributed. You can see that we're doing very well in Europe, and we're doing very well in North America, but we need to do a lot of work to reach the rest of the world. Partly that's bandwidth, partly it's localization. And so we've just started translating and crowdsourcing the translation of our sites. And we're beginning to see this have some effect. So putting the sites in local languages turns out to be hugely important. But what I want to talk about for the rest of my time, and we can argue about how much time I've got left when I see where we are in 15 minutes' time, is about going beyond what I presented so far. So far you should have got from this talk that there are a vast number of scientific fields where microtasking, where asking questions about images, easy and hard, is worth doing. And that there is a large audience of people out there who are engaged in those tasks and who can be distracted and can find the unusual stuff. Yeah?
There seems to be an enormous gap between the actual scientists and the citizen scientists. One doesn't seem to be exploiting people, say, at school who study science,
sure,
or undergraduates who study science. It's either a PhD
or it's clicking on some buttons, and yeah, that's what the second half of the talk's about. So, it's nice when a structure works for at least one member of the audience. And so to give you an example of people sitting in that gap, I want to use an example project called Planet Hunters. So Planet Hunters does what it says on the tin. It's an attempt to find planets around other stars. And we do this by looking at data. This is a graph that shows, it's from a satellite called Kepler, which for about 3 years recorded the brightness of about 150,000 stars every 29 minutes. And so this is the brightness of one star over time. And I don't know if you can read the axis, but it's an incredibly accurate measurement. So from the top to the bottom of this graph is about 0.5%. So this is a ridiculously accurate measurement. Most of it is noise, of course. It's either camera noise or the star may be fluctuating slightly. Stars aren't completely constant in brightness. But you can see in color here there's a dip. There's a sudden dip in brightness. And that dip occurs not to do with the star, but because a planet has got in the way of the star as seen from Earth. It's what we call a transit. And if you see a repeating pattern of those transits, then you can deduce that there is a planet there. This is how most exoplanet discoveries are made these days. And in some ways, it's an obvious machine learning task. and it's true that most of the planets, about 95% of them, have been discovered by machines, but we're still in the state of science. The first planet around another star was discovered only 20 years ago, so we're still in a state where no planet should be left behind. And so checking that we've got the unusual and the difficult ones is really important. And Planet Hunters has contributed to that. For example, finding the only planet that we know of in a 4-star system. So 2 pairs of stars, each in orbit around each other, with a planet, a Neptune-sized planet, going around one of the pairs of stars. But what we've been really amazed by was the ability of the Planet Hunters community not just to mark dips like this, but to collaborate and do much more than that. So here is how a typical Planet Hunters discovery happens. This is Talk. Talk is our object-oriented discussion environment that we built. So you go from classifying to immediately being able to discuss what you've seen. And what that does is it creates a information network so that people who are maybe just beginning could see something unusual. They can ask a question about it, and then we have a whole host of people who've become experts who hang out on Talk. And so that's what's happened here. This curve in the top right, see there's a dip there, was identified by somebody who was new to the site, and they said, oh, I think this is interesting, but what is it? And Kyan Jin here, who's one of the regular classifiers, has said, congratulations for a nice discovery, looking very good. He's gone to the NASA website, downloaded the rest of the data for this star, has identified a periodic and repeated transit. He folds it, so this is the sum of all of the transits. Then he looks in closely, and he says, based on an estimated depth of 0.0018%, we have a 3.8 Earth radius planet with an orbit of 0.4 astronomical units. The observed transit duration is 12.7 hours, which is much longer than the calculated central transit. So it's possible that the planet's in an eccentric orbit and the transit is observed close to Apastron, which is furthest from the star. This is somebody who a month earlier didn't know any astronomy. Okay, and they've become an expert in this field. Kyan Jin he's a computer scientist by training, but has put his training away and is now writing guides for how to do this in Excel, because Excel is the tool that his fellow Planet Hunters have access to. And we found this is a remarkable thing, in that the pace of discovery for Planet Hunters comes from somebody noticing something odd to an increasing network of expert volunteers who then send us an email. And we've literally been able to sit back and pick up these discoveries. And we now have 3 confirmed planets and about 100 planet candidates, 95% of which will be real, based on the statistics. So this is, it's really rather exciting. However, for a normal audience, this is where the talk stops. And I talk about the fact that I've shown you that in Galaxy Zoo, I've asserted that in Galaxy Zoo people are learning stuff and being inspired to learn stuff, and here we have a bunch of people who are applying that knowledge, and we're accelerating scientific discovery as a result. However, the percentage of people who are working at this level is incredibly small. So half of our volunteers will say something on Talk at some point during their Zooniverse career. The fraction of them who are engaged with this sort of stuff is rather low. I think it's worth thinking about why that is. In fact, we've tried to change it. So we ran a project, for example, called Galaxy Zoo Quench. Galaxy Zoo Quench had the slightly off-putting subtitle, Experience Science from Beginning to End, which we hasten to add is not the beginning to end of science, but of a scientific project. So Quench started as a standard Galaxy Zoo task, was a classification task looking at galaxies that had just survived a merger. And something like 20,000 people took part in that task. It was a relatively small amount of data. And then we provided a set of tools for them so that they could examine the data that they had collectively produced. And about 2,000 people used those tools to make significant discoveries. So they discovered correlations between things like the mass of these galaxies and what happened to them during the mergers. So imagine that, so by the end of that process, collectively, 2,000 of those people had agreed on a set of figures. You could give a conference talk using the results that they'd got to. And then the idea was that the last thing would be that some subset of that people would get together and write up this result for publication. So that while we were aware we wouldn't get all 20,000 people to go all the way through, that we'd provide a structured framework, a sort of beginner's guide to being a scientist, that would take people who started off as science attentive with no training through the stages to being published scientists. About 200 of the people decided to have a real go and try to have a go at collaborating on producing a paper. And their efforts are interesting, and there will be a paper that comes out of this. We're still working on it, but it wasn't the success that we'd hoped. That step, I expected the difficulty being in talking about how to manipulate data and how to understand the tools of big data and big science, and to understand what a statistical correlation is and so on. Wasn't that? The difficulty came, and it was a hard wall when people ran headfirst into the literature, both in terms of producing papers, but also in understanding what was already there. And I suddenly realized that the Zooniverse has this nice radical tale of citizen science and this nice wonderful story of increasing public participation. But from the outside, we're an incredibly conventional scientific project. We produce, because we want careers, standard scientific papers. I'm very proud of the fact that Galaxy Zoo now has more than 60 published papers that look like this. There are some nice tweaks. So that star on the title links to a full author list online, because the journals aren't really keen on author lists that have 600,000 people. OUP have made all Zooniverse papers in their journals open access from the beginning, because there was a demand from the volunteers to have access to the real thing. And so these are, the Galaxy Zoo papers in particular, appear often on the monthly notices of the Royal Astronomical Society, the major UK astronomical journal, list of most downloaded papers. And to my colleagues, I obviously claim that this is because of the quality of the research, but it helps if you have 600,000 collaborators who want a copy of the paper. But what's interesting, but that's about as far as it goes. Even reading these papers is a significant barrier for most of our citizen scientists. And for this audience, you'll already have got there, but it's worth noting this isn't about open access. I have lots of thoughts about open access. You can read lots of them at theoj.org if you don't know that project. But all of astrophysics is on AstroPH, on archive. And so access to these papers, for at least the last 30 years worth of astronomy, is open to all of our citizen scientists. And yet we see almost no evidence of engagement with the literature. And we spent a lot of time thinking about what might be causing this problem. Because without access to the literature, it's very hard to function in today's scientific ecology. Even simple stuff like the planet hunters who are doing that amazing advanced work. What they want to be able to do is they want to email experts in the field. In particular, planet hunters found not just a whole set of planets, but they found all sorts of stars that were doing interesting things, that were varying in brightness in all sorts of interesting ways. A good example is a set of what they call heartbeat binaries, where the brightness versus time graph looks like an ECG. And it's caused by two stars which are orbiting so closely that they set up tidal resonances in each other. Now, only 3 of these were known. Planet hunters have found another 30. And so they want to email the world experts in heartbeat stars and say, hey, we found another 30 of these things. But if you lack the language that you get from learning the literature, it's very easy to get lost when communicating with a busy scientist. Academics, as I'm sure many of you know, think we're the busiest people in the world. And if you get an email from a colleague that says, hey, I saw your paper, I see in figure 6, you've got this relation, here are my discoveries on the same relation, let's talk. You respond to that. If you've got a 6-page email from somebody that says, my friends and I are on planet hunters, and we think we found this thing, but we're not sure, it's a huge impedance mismatch. It's a huge barrier to communication. What I think is going, so this question of why our citizen scientists who are engaged and who do care about real science are not reading and not engaging with the literature. And I think the best analogy I've got is with the museum world. This is the front of the National Gallery in London, and it's a typical sort of 19th century museum facade. It's there to project power and grandeur and impressiveness, right? That's why these big public museums were developed. That creates a barrier to entry. There's a concept in the museum world called threshold fear. And the idea is that if you run a gallery like this and you want to increase the diversity of your audience, it actually doesn't matter what you do inside the building. No matter what exhibitions you put on, no matter what labels you write, no matter how many innovative ways you come up with to navigate through your collections for the non-art historian, the only people who are going to go through this door are people who've already decided that they can get something out of the experience. People, for the most part, that look a lot like me. And indeed, you can see this in the UK, when the National Museums were made free. For the first few years after that happened, visitor figures went through the roof, but it was the same people going more often. After 10 years of this being free, that's not true. But it took 10 years for people to get used to the idea that these museums had something for them and that they could be wandered into. So I think what the literature is presenting to our citizen scientists is a threshold fear. I think people take one look at something like this and say, oh, this isn't for me. The only people who read scientific papers are people who've already decided that they can get something out of them. And this is why even excellent or well-meaning efforts to try and translate the literature don't succeed. I'll give you an example. So I was a big fan of a project called ScienceWise, and ScienceWise built on top of the archive, and you could go through and create a tagged PDF. Instead, I know this is, sorry, it's a PDF. But the point is that your paper then looked like this. So it was a nice interface for taking every technical term in the literature and it linked to a definition. And you could either accept a standard definition or you could write your own. And we did that for most of our papers and found almost zero take-up of this. So the idea was that you would read through this and then you'd click on anything you didn't understand and you got a definition. And this didn't work. And I think it didn't work because it's rather like having training wheels on a bicycle. You know, if you've already decided you really want to ride a bike, then you'll put up with having training wheels for a short amount of time. I mean, if you remember learning to ride a bike as a kid, I couldn't wait to get rid of the training wheels, but I accepted that that was part of the process of learning how to ride a bike. If you're not sure, say you're learning as an adult, whether you want to learn to ride a bike or not, you don't want to try the thing with training wheels. You can see that's not the real thing. And I think that's what's happening. This isn't a way over. It's a teaching tool. It will help with undergraduates and so on. But it's not a solution to this threshold fear problem. However, there are solutions out there, I think. I was very struck by PLOS Medicine, which I think for all the papers, but certainly for a large fraction of them, the first thing you see when you go to the paper, you got the abstract, there's an editor's summary, which is written as a lay summary of the paper. And what I like about this is it's part of the paper, right? It's easy to stray from reading the editor's summary into reading the introduction. It's the next section. It feels like part of the real experience. You've gone to the journal and you've received some information. I think this sort of thing can seriously help us break down the barriers, and it's not difficult to do. There's no technology here, it's just more text. What's difficult here is scaling this. For PLOS Medicine, I believe the editors write the editor's summary. And because it's a high-quality journal, there are few enough papers that they could do that. But what we need to find is a way of getting authors to write this stuff. So I would like to advocate that for most journals, I'm going to talk to the astronomy ones about doing this, that you should be required to submit not just an abstract, but a lay summary. And we peer review that. We peer review it maybe with some of, maybe experts in the field, but maybe somebody from outside the field needs to take a look at that and review it for whether it's acceptable or interesting, or indeed summarizes the paper accurately. I think that would go a huge way to breaking down this barrier, because it brings some of the content out of the walled garden, out from under that 19th century portico, and into places where people can encounter it. Other models exist as well. We could perhaps, in some sense, crowdsource the writing of lay summaries. So there's an excellent website called Astrobytes, for example. It started as a project at Harvard. These are summaries of papers written by astronomy graduate students with the target audience of undergrads who are beginning to do research. And they're brilliantly written. And there's clear advantage here for the PhD students. They get a chance to practice scientific writing, they get a chance to read some more papers, which is always good. But we could attach this to the paper itself. And so other examples exist. Now, I am on my time, but I have another set of stuff I want to talk about. I'm looking to the chairman to tell me whether I should shut up or not.
You should carry on with this.
All right, fine. I like this conference. So this, I think, is the solution to engaging with, or half of the solution to engaging our audience, our large citizen science audience, with the tools they need to take part in scholarly communication. But we can do better than that, because we can also go back into the places where they're doing citizen science and try to find the natural experts, the people who could make these contributions or would benefit from this, because a prompt will be useful. Being able to say, hey, you should read this is much more effective than saying all of you have access to all of the literature. So we've been doing experiments in this field. This is one of them. This is Zunibot, as drawn by the daughter of one of our volunteers. Zunibot participates in discussions on the Planet Hunters Forum. And what he does, he's a result. I don't know why I've decided it's a he, and we can discuss gender of robots over a pint later. Zunibot is a solution to the fact that when we talk to people who are taking part in conversations on Talk, they tell us that the main thing they want to do is have contact with a scientist. Right? They ask a question, they want a scientist to answer. That's straightforward. I just hit scientists until they take part in the conversation. We've already seen that there are scientifically useful discussions on Talk. However, from the data, the #1 predictor of whether a conversation will stop is participation of a scientist. So it's rather like the voice of God appearing in the middle of a discussion, right? You're having a happy discussion about whether this is a galaxy merger or not, and I come in from the University of Oxford and say it's a merger. That might be an intrinsically satisfying thing for a moment, but it kills the conversation. And so Zunibot is an intermediary. So Zunibot is slightly miserable. Credit to Douglas Adams. So Zunibot, so what's happening here is this is an expert user. So this is an interesting style. You can see it's got a strange pattern of variability. And the first user at the bottom here, H. Smith, 1914, is an expert, and has come along and said this is an obvious GDOR. Now what's interesting about this is that's a technical term. It stands for Gamma Doradus. It's a type of variable star. But if you Google GDOR, that's not the abbreviation that professional astronomers use. You won't find a definition of that anywhere. It's a culturally created definition amongst the Planet Hunters community. And so Zunibot knows that. So Zunibot says, I am Zunibot. The people who helpfully programmed me have asked me to say at this juncture that a GDOR is a Gamma Doradus variable, a type of star that undergoes periodic variations in brightness, and there's more info here for what it's worth. And it turns out that this doesn't put people off. This isn't the voice of God, it's a slightly bumbling robot. And what it's doing is it's providing a translation service between experts and non-experts within the forum. And it's much needed because we can present results like this. So this is from a project called Seafloor Explorer, which is looking at robotic images of the seafloor off the northeast of the US, looking at fisheries health. And on the left, you've got the stems for the most common words used by volunteers during their first 10% of comments on Talk. And now, what do you think? This is a fish? Is this a scallop? I don't know what this thing is. Tell me about this image. Is this a sea star? And so on. And on the right, you've got the list made by, these are the most common stems for people in the last 10% of their participation in Talk. And I do not understand what most of these words mean, because this is not my field. Penguins I can bluff, but this stuff is not easy. But this is a failing project, because what this shows is this is a concentration of discussion amongst a small group of experts. So people who can take part, can use these words, are doing so and are hanging around, but everyone else is leaving. And so we must bridge the gap between the people who use the vocabulary on the left and the people who do this vocabulary on the right in order to be able to cope with the scale of future data sets. So we can identify using language on Talk both places where we need to intervene, but also who the experts are, and we could point them to the literature and to other opportunities. We can also use their participation in the projects themselves. So this is a project called Space Warps, where we were looking for distant galaxies whose light has been bent by passage through by a nearby galaxy. They come up as these little blue arcs around the galaxy. And what's nice about this project was it was really easy to put in simulated successful searches. So if you find a simulated one, we can give you feedback. You can say, yes, you found a simulated lens, well done. And we have some blanks as well. We say, actually, we know there's nothing in that image. And this allows us to assess what's going on with individual classifiers. So here are 50 random spacewalk classifiers. This, on the x-axis, is the probability that they say there's something there when there's something there. And on the left is the probability that there's nothing there. They say there's nothing there when there's nothing there. And so the best people are up in the top right. And you can see this is quite a good project. There are lots of people in the top right in what we call the astute classifiers. We also have people in the bottom left who we can call the obtuse classifiers. These are people who are wrong almost all the time. But the nice thing is that if you know somebody is wrong all the time, they provide precisely the same amount of information as somebody who is right all the time. Many of you may use this technique in your professional lives as well. But this means that we can make use of these people. We can also split people on the right who are optimistic from people on the left who are pessimistic. And you can start to think about how you might use that. For example, if I have an image where I'm pretty sure there's something there, maybe what I should do is show it to a pessimist. And if they say there's something there, then I should be very confident in that detection. And you could programmatically look at that. We have a full Bayesian model of classifier and classifying behavior to do this, which greatly increases accuracy. But that's not the point, because I know the point here is that I can find these experts. This is a very complicated graph that I want you to mostly ignore. But in the bottom left, this is from an upcoming Spacewalks paper. But in the bottom left here, this is the amount of effort put in, so the number of classifications that have been made. So people on the left have done few, and people on the right have done essentially the whole data set. Then if you look at the third graph up, where it's called skill, skill is the information contributed, literally the Shannon information, the information contributed by classifiers who've put in that amount of effort. And so you can see that we're doing a good job. There's nothing down here. So no one is doing a huge amount of classifications and not producing anything useful. So this shows that our training is doing okay. But the thing I find most fascinating, and there are people down here who've done a few and aren't very good, and there are people up here who've done a lot who are very good, but the people I find fascinating are this lot. These people are very, very good at this task. They provide as much information as people who've done classification 100 or 1,000 times as many classifications as them, but they left the project. To me, those are experts who we can engage in different ways. Those may be the people who have the expertise, who aren't necessarily just citizen scientists, but have some technical expertise, or indeed just have confidence that they've got from wherever. But those people, if we could find them early, and we can do this sort of detection in real time, then my question is, where do we send them? What do we say? Do we say to them, well, look, if you want more background, go and read these papers, or could you summarize this paper, or could you find people in the community who need your help? Because these are people who are not being engaged by the basic task, but who demonstrably have skill. And we need to care about this stuff. We need to care about this stuff because citizen science is going to have to get more efficient because of things like this. This is the mountaintop in Chile being leveled about a year ago, and it's being leveled for worst Photoshop ever. This is the Large Synoptic Survey Telescope. This is the Next Generation Sky Survey. LSST will scan the whole sky every 3 nights. It's as big as the biggest telescopes that we have today, and it will produce a reduced data set of 30 terabytes a night released onto the open web for anyone to use. But then in context, if all you care about are things changing in the sky, and you subscribe to an alert stream from LSST, a conservative estimate is that you're going to get a couple of million alerts a night. And in filtering that stream, we're going to need efficient and clever ways of engaging a whole community of citizen scientists. And in fact, we're back to the 19th century problem. One of LSST's goals is to really nail the study of variable stars. And that was started by this guy, a German astronomer called Arglander, who wrote in 1860 in an appeal to amateur astronomers to send him observations. He said, Could we be aided in this matter by the cooperation of a goodly number of amateurs? We would in a few years be able to discover laws in the apparent irregularities and the variabilities that in a short time accomplish more than in all the 60 years that have passed since their discoveries. I've got one request, which is this, that the observations should be made known each year, for observations buried in a desk are no observations. And should they be entrusted to me for reduction or even publication, I shall undertake it with joy and thanks, and will also answer all questions with care and with the greatest pleasure. And the way I see the challenge that I've tried to describe today is finding a way to build the tools so that modern scientists can undertake the task of collaborating with millions of citizen scientists with joy and thanks, rather than stress and too much email, and a way for a system and a set of scholars to answer all questions with both care and the greatest pleasure. Thank you very much.
Thank you very much, Chris. We'll take just one question, then we're going to break for coffee. So is there a burning question? Yes. Yeah.
Hello, I'm Danny Kingsley. I'd like to introduce myself to the UK. I started as the head of scholarly communications last week in Cambridge. My question. It's not so much a question, but an observation in relation to both of your solutions to getting information out and becoming the bridge. You're talking about a science communication solution to a scholarly communication problem. And as somebody who used to be a journalist and then became a science communicator, then did a PhD in science communication, now works in scholarly communication, I spent a lot of time talking to PhD students about this issue, about sharing your information. Their first response is, why would I want to tell anybody else other than other scientists? That's my audience. So you get that first. And then the issue about trying to tell them that what you need to explain is the importance of your work, the who cares factor, and try to turn it upside down. So don't end with the punchline, start with the punchline. And so this is quite a hard thing. By the time they get to PhD, they are so ingrained in scientific writing, it's almost impossible for them to get their heads around. You do get there, but it's a lot of work. And I think it's quite important to think, universities to think about this as actually part of the training of our PhD students. It's part of their professional development. That's my observation.
Thank you. Chris.
So I think you've stolen my microphone. So if I'm loud, can people hear me? Yeah? Excellent, thank you. Yeah, I agree with all of that for many reasons, except that I think I'm trying to say a couple of things that are different here. So what's interesting about these projects is that they don't feel like normal science communication. I do a lot of psychoms. But what you're doing here is because both sides are aligned on the detail, one of the weird things that this does is it creates an audience amongst the citizen scientists for the detail, the arcane detail. So you actually don't need to make that argument about why do we care about this. What our volunteers want to know is, why is the cadence for Kepler, why does it take a measurement every 29 minutes? So you could skip past the why do we care about exoplanets stuff, and suddenly you're in the details. So it's a form of science communication that some people find much easier. And it also answers that question of why am I doing this? Because it accelerates the process of research. And so I think that there are differences, although of course more training would help. The other thing is, something I meant to say explicitly and didn't, is that I think in designing a set of scholarly communication tools that work for citizen scientists, I think we design a set of scholarly communication tools that work better for scholars. I certainly don't read in the way that my volunteers think you read a paper from beginning to end and you stop and look up every word you don't understand. I haven't read a paper like that in 15 years, right? You read the introduction and then you look at the figures and then you argue about it a bit, and then maybe you have to read the methods and so on. And there are faster ways of doing that than pretending that you're going to read a whole paper from beginning to an end. So I think this lens is an interesting way to think about how we want to browse papers and how we want to browse the scholarly literature as well.
Thanks, Chris. There's a quick question from Dan. And
yeah.
Then,
Dan Ketz from the University of Chicago. A quick question. I heard Peter Nugent give a talk a couple of months ago, and he was describing a citizen science project where they were comparing citizen science and machine learning, and they ended up deciding that machine learning actually was doing a better job than people once they had used the people to train the machine learning techniques. And so I guess I'm wondering if you can talk a little bit about kind of how you see the role of citizen science versus machine learning, and if it's problem specific or how they blend together?
Sure. I mean, that was one of our projects that you were talking about. And so a good outcome for a Zooniverse project is that it puts itself out of business by creating a large enough training set that the machines can take over. However, that's hard. One of the things that's happened in machine learning is that the kind of deep learning approaches that people have gone for rely on insanely large training sets. And so we just ran a competition for machine learning people to attack the Galaxy Zoo problem. And one of the huge bits of feedback we got was that we'd only given them 250,000 galaxies to train on. And so large training sets are best generated by citizen science rather than professionals, but also so hard to do. However, once you get into this game of optimizing, of saying, you know, should I give this to a pessimist or an optimist right now, and of measuring classifiers, there's nothing that stops you mixing machines and humans. And we're building systems now that do that. So based on what I understand about this image, based on who I've got online and what machines I have available, who should I send it to? And my bet is that if you do that, you'll get into a mode where what you're really doing is sort of generating training sets on the fly. For LSST, my guess is the start of every night, conditions are different, the telescope performance is different, the camera noise is different. So you'll probably start the night by needing lots of humans. And then over time, you'll generate a very specific training set for those conditions. And by 2 a.m., it'll be the machines who are taking over. So I think there's a role for both. And the trick is to be smart about how to do that. I'd love to talk more about it. I've got a whole hour talk about that stuff. But it's not as simple as having to choose between one or the other.
Thanks, Chris. Thanks, Dan, for a good fourth quadrant question as well. I know there were one or two other questions.
Just a quick, hi, Anita de Waard, Elsevier. A quick follow-up on this whole point of scientific writing versus writing for larger audience. There's a huge literature out there on discourse comprehension of scientific text. And what's quite clear is that students, as they become scientists, they learn this sub-language, and it has specifically a specific syntax. There's a lot of nominalization, there's a lot of, so it's not the words that are hard to understand, it's the syntax itself and the structure of the paper. The reason you and any other scientist can glance through it is because you've been trained in the schema, and you've been trained in the syntax to recognize the right points, and that's just a learning process. And similarly, I agree, it's very hard for people who have been trained in that to unlearn it and to rethink about this topic in a very different type of discourse. That's a separate skill set that most scientists haven't learned, but also don't have. So there's very interesting books and writings on this. If it's something to pursue, I think the crowdsourcing the abstracts is a fabulous idea.
Thanks, Anita. That's a good fundamental point about scholarly communication for the fourth discussions.